Hello everyone, I'm Norman Wildberger. We're looking at the sociology of pure mathematics, especially now at number systems and trying to position the way we think about numbers in terms of sort of a broader picture of historically what's been going on. And I've been telling you about the Egyptians and the Babylonians, and I want to clarify a little bit the Babylonian situation because that's very interesting. And it's not so easy for a sociological type person to get a hang of what's going on there, because there are these obstacles that, first of all, we're talking about an entirely different culture, and the way they approach arithmetic is very different. But even more so, the fact that they're working in this base 60 system means that most of us don't have a lot of experience with that arithmetic. So I'm going to propose a variant of our arithmetic today, which will be a great aid, I am sure, in being able to understand more clearly how the Babylonians thought. Or at least this is my attempt at doing that. Okay, so I'm going to introduce what I call centimal or base 100 arithmetic. So this is a new sort of point of view, but it's not just changing the base. I'm also going to go back to an old Babylonian point of view. So let me remind you that with our ordinary Hindu-Arabic numbers, which of course is a base 10 system, here's a big number. If I want to read this number, I'm going to look at it, here's ones, here's thousands, there's millions, there's billions, there's trillions. After trillions comes quadrillions. So I would read this as 67 quadrillion, 149 trillion, 25 billion, 488 million, 665,000, and 313. And when you hear that, you start to realize that actually our number system is not just a base 10 system, it's also partially a base 1000 system. Because each of these sort of triples here is in some sense a digit between 1 or between 0 and 999. So we have sort of two levels going on here, the base 10 level and this larger base 1000 level, which is usually not really acknowledged, but you can see it very clearly here. So what I'm going to propose today is in some sense a kind of a compromise between base 10 and base 1000. We're going to look at base 100, okay? But I'm going to approach it in a true floating point fashion, just like the old Babylonians from around 1900 to 1600 BC would have proceeded with their sexagesimal system. So by getting our head around this system, it'll be much easier for you to appreciate the remarkable base 60 system that they had. Okay, so base 100, it means we're going to have digits from 1 to 99. The old Babylonians did not have a special digit representing 0, so that's actually excluded in our world. Just digits from 1 to 99, what we call 99. Now, this is the way that a Babylonian scribe would approach that problem. Well, we use the two symbols that the Babylonians used, a vertical stroke representing 1 and a wedge opening to the right representing 10. So then here would be the digits 1 through 9, there would be 10, this would be 11, 12, 13, 14, and so on up to 19, 20, all the way then eventually to 30, then eventually to 90. Right, in the sexagesimal world, you're not allowed to use 9 tens. The maximum number of tens that ever appear is 5. But this is centimal, so it's a little bit bigger. So we can go all the way up to 99. Okay, so these would be the 99 digits that a Babylonian scribe would want to write down for our system. But this is too onerous, okay, so it's a lot easier for us to use the standard Hindu-Arabic numbers that we are familiar with, 1 through 99. Although, it might be easier for us, but for somebody who's not familiar with this system, it would be probably harder, and maybe this would be sort of simpler and easier to understand. Okay, so then what is a centimal number? Well, a centimal number is just a string of these digits put together, separated by commas. And we'll use commas because that's a little bit more in keeping with what I showed you in our first slide, where we had these groups of 3 decimal digits separated by commas representing thousands, millions, billions, etc. So I want you to think about this as being some kind of variant of that. Instead of grouping things by groups of 3 with commas, we're separating with groups by groups of 2, all right? But it's a true floating point system. So you should not think of this as being the ones, and this is the hundreds, and this is the 100 squareds, etc. That's only one possibility. We're not saying where the decimal point, or rather the centimal point is here, right? That's just a centimal number that can be interpreted in a number of different ways. So now that we have centimal numbers, which are just these strings of centimal digits separated by commas, we can maybe convert them to our more familiar decimal Hindu Arabic numbers. But there's a number of ways of doing that depending on where we think of the decimal place as being. So that's not specified in the centimal world. So this centimal number 5, 43, 92, 17 could be interpreted, well, one way would be to think of this as being like ones. This is hundreds. This is 100 squares. This is 100 cubes. So then we would just get 5, 4, 3, 9, 2, 1, 7. So that's directly just translatable. That would be 5,439,217. But we could also perhaps think of the centimal point, if you like, as being there, in which case this would be sort of representing the integer part, and this would be representing a fractional or centimal part. Then it would correspond to I guess 54,392.17. Or maybe we think of the centimal point as being right there, and then the interpretation will be 543.9217. Okay. Now, one of the advantages in having this flexibility where we're not actually thinking about having a centimal point is that multiplication becomes simpler, because we don't have to worry about where to put a final centimal point, because there is no final centimal point. So let's talk about multiplication. So suppose we want to multiply these two centimal numbers. Okay, 2317 times 4152. How are we going to find out what that is? Well, what we're going to think about is doing essentially a number of multiplications of just single digits. So these digits here, this 52 and this 17, if we multiply them, we're going to get 884, okay, which corresponds in our language to 52 times 17 equals 884. Okay, but as a centimal scribe, we would say 52 times 17 equals 884. Another product, 52 times 23. Well, just that product by itself is 1196. 41 times 17 is 697, and 41 times 23 is 943. So these are just perhaps you might like to think of them as sort of entries in this 100 by 100 multiplication table that records all possible products of digits here and digits here. Actually, for us, it's not really 100 by 100, it's more a 99 by 99, because actually 0 is not allowed as a digit. Of course, these just correspond to familiar or easily checkable things in the Hindu Arabic world. So 41 times 17 is actually 697. So, you know, it's the same kind of information as we usually have. So that makes it a lot easier to understand what's going on. So how are we going to multiply these two numbers? Well, we have the individual products of the digits, so we are going to kind of wanting to put them together. So that's our inclination, is to, you know, figure out how to do it on the page. But almost surely that's not how they did it. They did not do their computations on their clay tablets. They did their computations somewhere else, and we don't really know. So the best guess is probably that they used something like an abacus. Okay, so here's a more modern abacus, but we can still just use it for illustration purposes. So what we're going to do is think about putting a number on the abacus sort of from the right. So because, you know, we're starting with the smaller things here and they're going to move over here. So for example, 2317, we'd represent that with a 7 on the last column. Okay, maybe these are 5s, let's say, and these are 1s. Okay, so we would move one of those up, and that's a 5, and then two of these up. Okay, so So that would be like 7. So I've recorded a 7. And then in the next digit of 1, I would put a 1 there. No, if I just wanted to record 23, 17. So there's a 17, and then that's 5, sorry. That's 1 there, and then 3 there, whoops, 3 there, and there's 2, okay? So that might be a representation of 23, 17, sort of roughly something like this. Okay, so in order to make this product, they wouldn't have to actually put these things down because these would be on in front of them. We want to write down the result. So let's say we multiply 52 by 17 first. So we figure out somehow, maybe we've memorized it, maybe we look it up somehow, but we have to know what the basic digit multiplication is. So in this case, it's 884 or 884, but we'll just think of it as 884. So we have to record an 884 on the last 3 of these columns. So we put a 4 on this one, and an 8 on this one, and 8 on this one. And then we do another digit multiplication, say 41 times 17. And or maybe 52 times 23, that's that 1196. So now we have to put 1196. We have to add 1196 to what we already have with our 884. Now that involves moving over 2 because we're moving over a digit, and so we have to basically move over a digit. There's actually commas here, which I perhaps should put, but I'm not putting them. Okay, so that means that this 1196 is going to be added, and we're not going to use these last 2 columns here. We're going to add that, in these columns here, these 4 columns here. So we're going to take the existing stuff and add 1196 with whatever abacus technology we've learnt, okay? And then that's going to be the total up to that point. And then we do the next digit, maybe 41 times 17, which is 697. So then we would have to add 697 again. That actually would be aligned to the same one as before. So I guess it would be still those 4, or these 3 in this case. So we would be adding something to these 3 columns to add 697. And then finally, the 41 times 23, that's 943. So we have to add 943 again. But again, we have to sort of move over the right number of columns. 2, 2, so we have to move over 2, 2. So we'd sort of be adding from here. Okay? So we could do that. And it would, if you're skilled with an abacus, of course, as in previous generations, many Chinese, Japanese, Korean, people, students would have learned, they can compute with an abacus much faster than we can compute by hand with pen and paper. So it's a very powerful system. There's no reason why the Babylonians could not have mastered the use of something like that, although we don't know exactly what they're doing. So I'd like to compare that with the same calculation in a more familiar Hindu-Arabic framework. This is what you might find in some primary school classroom, where the way we do it is we also multiply digits, but now the digits are just from the 10 by 10 multiplication table, which we've memorized. So 2 times 7, you have to know what that one is. So it's 14, there's a 4 there, and 1 comes up. So you have to do all these individual products. 4 times 4, 16 individual multiplications have to be sort of put into this. Okay? But the individual multiplications are smaller because they're just sort of single-digit multiplications. So here we only have 4 digit multiplications, but any one of them is more onerous. Of course, we end up getting the same total. Maybe I should also have mentioned that once we get these digits, we've done this on the calculator, okay? But this is my attempt at doing it by hand using paper, the way we've been taught. You have to add up the columns and so on. But they wouldn't have done that. They would have just, done it on their abacus or counting board or whatever, and then looked at the final result and then just transcribed the final result. So notice that when I go from this to the final result, I have to modify this 0, 1, because 0, 1 is not a digit in our system. We have to just replace it with 1. So the final answer is 962, 184. And here's the Hindu-Arabic equivalent. And, okay, which one is more work? Well, they're pretty close to being comparable, but you see that they look quite different. And so I think it's an interesting computational question here for those of you maybe with a computer science programming background. Can we say anything about the relative merits of these things, right? There's a trade-off. Here we're doing a lot of small calculations, and here we're doing fewer big calculations. So there's probably scenarios where each of these maybe has advantages. But I think it's interesting to think about this sort of from a computational point of view. Could you get some computer architecture which runs not on a sort of decimal or binary equivalent, sort of arithmetic, but that jumps up to centimal or some kind of binary equivalent? Maybe they already do this. That could be. Please let me know if that's the case. All right, but a big question here is, how do you actually multiply these digits? Do you memorize a 99 by 99 multiplication table? Well, this is the same issue that we have with the Babylonian story. There it's 60 or 59 by 59, but it's still quite onerous. And I remind you that we don't really know how they do their multiplications. We don't really know. But we think that we have some ideas. And one of the ideas is to use this particular relation, which was well known to them. That if you have two numbers m and n and you're interested in their product, m times n, then one way of getting at it is through this identity, that it's equal to n plus m over 2 all squared minus n minus m over 2 all squared. So for example, with 41 times 23, if we're going to use this rule, we calculate, this is the average. So you add them up, which is 64, and divide by 2. So that's 32. This is 32 squared. And this one is the difference divided by 2. Okay, the difference is the difference is 18, and divided by 2 is 9. So it's 9 squared. 32 squared minus 9 squared. 32 squared, well, you have to look that up, or let's say you know that. That's 1024. 9 squared is 81. You take the difference, you get 943. Now, here's a way of thinking about that. Here's m and here's n. Let's suppose that m is smaller than n. Okay, so the average is just the number that's in between them, that's equally far from either of them. And this n minus m over 2, that represents, well, this whole difference is n minus m. So n minus m over 2 is that separation or that separation. So another way of thinking about it is that this second one is the separation between either of these numbers and this average. Okay, so for example, once we've found that the average is 32 up here, then the next one, we just look at the difference between 41 and 32, that's 9, or the difference here, that's also 9. Okay, so we don't actually have to do this calculation so much. But what do you do when you are multiplying, say, an odd number by an even number? So this works fine if you have two odd numbers or two even numbers. What if you have one at each? Say 29 times 84. Well, what you could do is you could, because what you don't want to really apply this formula, because then you get, when you add these two numbers, you can get an odd number, and then you have to divide it by 2 and square it. So that's more problematic. So you could pull out a factor of 2 here, write it as 2 times 29 times 42, and then you could, in fact, pull out another factor of 2, write it as 4 times 29 times 21. And now you have two odd things, so you could do the same thing as the rule suggests. You take the average, which is the number that's sort of equally close to both of them. That's 25. Okay. The difference between 25 and either of these is 4. So 25 squared minus 4 squared is 625 minus 16, which is 609. And then we have to multiply by 4. We get 2436. So what this rule allows us to do is to reduce the calculation of a product with calculation of two squares. Okay, so if we're on top of squares, or if we, have some table or resource that tells us quickly what squares are, then we can actually use this quite efficiently to calculate products. Okay, so now we come to the table of squares, which is an essential table for the old Babylonians. It will also be important for us as modern centimal arithmeticians. So we have numbers down here and their squares adjacent. Numbers and their squares, numbers and their squares. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared equals, well, not 100, because there isn't really 100. It's just 1. Okay? That's the way the floating point of view is toward. 100 and 1, they're the same thing. They're just represented by a single vertical stroke. What about 11 squared? Well, 11 squared is 121, 1, comma 21. 12 squared is 144. 13 squared is 169. 14 squared is 196. 15 squared is 225. 16 squared is 256. 17 squared is 289. 18 squared is 324. 19 squared is 361. And 20 squared is 4. These will be a little bit less familiar to most people. Everyone's memorized these in primary school. These are a little bit less familiar, but actually it's very useful to know what 17 squared is, etc. So let's do one more column. 21 squared is 441. 22 squared is 484. 23 squared is 529. 24 squared is 576. 25 squared is 625. 26 squared is 676. 27 squared is 729. 28 squared is 784. 29 squared is 841. And 30 squared is 9. Of course, this is information that you can immediately, value. This is the same as saying 24 squared is 576. It's the same information. In fact, 576 is often stated as 576, right? It's recognizably the same thing. Okay, and here's 30s and 40s. I want to draw particular attention to the last ones here. So once we get to 46 squared, it's 2116. Which ordinarily we would say 2,116, but it's just 2116. And 47 squared is now 22,9. But there's no 0 here because 0 and 9 is not a digit. 9 is the digit. Similarly, 48 squared is 23,4. 49 squared is 24,1. So if we wanted to convert this to decimal, we would say, okay, this is 2,401. We would sort of implicitly put a 0 in there, but that's not needed. And 50 squared is 25. Okay, and here's the second half of the table of squares. I'm not going to go through it all, but here it is for you to admire. 51 squared is 26,1. 52 squared is 27,4. We have that same phenomenon that I already mentioned. 53 squared is 28,9. And then 54 squared is 29,16, and so on. 60 squared is 36, the 60s, the 70s, the 80s, down to the 90s. 96 squared is 9216, 97 squared is 94.9, 98 squared is 96.4, 99 squared is 98.1, and 100. Why isn't this 100? Well, 100 is equal to 1 in our system. And so what's 100 squared? It's the same as 1 squared. 1 squared is 1. So involved here, if we're going to memorize this table, that would involve memorizing 99 things. And it's probably, interesting to stare at it and see if there's any patterns. I mean, there's some things that are sort of repeating, the 96, the 69. These things that are sort of happening here at the end there's some repetition. A square never ends in 3, for example, right? You never see the final number be 3. The final numbers are always rather predictable. In fact, they're the same across each of these columns. The final numbers are always 1, 4, 9, 6, 5, and then, or 6, 9, the same ones we just had, 6, 9, 4, 1. That's the table of squares. And so you could imagine that it would be possible for a young person to memorize this. There's really 99 things to memorize, although some of them are quite long. So it would be definitely some serious amount of work to memorize this. Then it's an interesting question. Okay, suppose that you got some young people and you trained them this way. You got them to memorize this table. Maybe you got them to perform digit calculations with using this device. You'd have to still teach them how to use some mechanical device, say an abacus, to deal with this centimal arithmetic. And so then it's an interesting question. Well, what would the result be? How would that compare with our current system? Is this really so outlandish, or are there actually potentially interesting reasons why we might want to go this way. Okay, so that's multiplication. What about addition? Well, we've already seen some addition because in the course of doing our multiplications, we've had to add these various products of digits that we've obtained. And what I did there is I put them in certain positions with respect to each other. And I was sort of suggesting that we're going to end up using our abacus or counting board or whatever it is to perform those additions, because that's reasonably easy to do with such a mechanical device. But from a theoretical point of view, it's important to realize that if you have two centimal numbers, say 44, 37, 2, and 98, 95, asking what is the sum, that's an ambiguous question, because we don't know the relative sizes of these things. So it's not so much a question of knowing where the centimal points are in each of them. It's more a question of knowing how the two centimal numbers align, where we maybe think of putting one on top of the other. So for example, one possible alignment might be this one here, 44, 37, 2, 98, 95. Maybe the 98 is comparable with the 44 and the 95 is comparable with the 37. Okay, then we can perform the operation with an abacus very simply, but on the board's much the same. 2, 7 plus 5 is 12. You put the 1 up there, you get a 13. You have to put a 1 there. You get a 13. You have to put a 1 there. You get 14, and you get this. So you get 1, 43, 32, 2. Let me do this one over here, which is just a little bit different. Okay, so two other things to add: 92, 86, 57, plus 4, 13, 45. And let's do the same thing. So 5 plus 7 is 12. I'll put a 1 up there. 4 plus 5 is 9, plus 1 is 10. So we put a 0 there, put a 1 up there. We get 7 plus 3 is 10, so we put a 0 there, 1. 8 plus 2 is 10, so we put a 0 there and put a 1 up there, and then we get a 7 and a 9. Okay, so we would put commas like this. But this really is not in centimal form for two reasons. First of all, 0, 2 is not a digit, and 0, 0 is not a digit. So what we would want to do is we would want to rewrite this. So there would be a 97, comma. Okay, let's think about what we're going to put in the middle here. But this final one is just going to be 2. All right. So what are we going to put in the middle? Well, the answer is we're not going to put anything in the middle because we don't have a digit representing 0. The Babylonians didn't have a digit for representing 0. They just left a space. Of course, they didn't have commas, but they just had these digits arranged in a line, and there were spaces between them. So if there was a sufficient amount of space, they would know that there's going to be, that's representing an absence of a digit. Okay, so okay, that might look a little bit strange to us, but hey, it's just a space. Our computers are capable of making spaces. Okay, so there's an introduction to centimal arithmetic, but we still have some ways to go because we still have to answer the serious question, how do you do division? And that's where things get interesting. So I'll talk about that in my next video. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.